All right, let's look at what happens when your cross section is a washer instead of a disc. Now, a washer is something like this. It's basically a disc but with a hole in the middle, and you get this as your cross section whenever the area you're rotating around the axis of rotation doesn't touch it. So let's look at an example, or better yet, let's look at an animated example on this tool and see what happens. I'm going to make up a just sort of a fun looking function. I'm going to do sine of x plus 1. Let's go from 0 to, let's say, 2 pi. Shade that area. And let's make that 0.3 pi and make this go from, let's make this start at 1. This at 2. All right, so that's the area we're going to look at. Let's take that and rotate it around the x-axis. So when we do that, we get this thing, and there's a hole in the middle of it. And each one of these cross sections is a big washer. So what we're going to do is we're going to have to find the volume of all these washers and add those up. And I made up kind of a weird example here because I wanted something that looked like that. I don't know, something that was interesting looking. Before we go back and work out the formulas, though, let's I want to rotate around one other thing. Instead of around y equals 0, let's rotate around y equals 3. All right, if I rotate around that, if I turn the opacity up, this looks like a well, on the outside it looks like a cylinder with a hole through it. But if you look in there, that hole isn't a uniform width all the way through there. I turn the opacity down and start drawing these in. You can see how the outer radius stays the same, but the inner radius changes. So anyway, let's work out the formula for this. All right, so what we've got is something like this. Let's say we're rotating, or better yet, I'm just going to draw the washer. It looks like this. And there are 3 things. You've got the thickness, and then from inside of here, you've got 2 radiuses. You've got that one. And what I typically do is I use little r for the inner radius, and I use big R for the big radius, the outer radius. So the volume of the washer, I want to talk about this a little bit, and then I'll write the formula down. But basically what you can do is take the area of the big circle and then subtract the area of the small one. I don't need to write all that out. You can do that. And so what you wind up with for the volume of the washer, it's pi times the big radius squared minus the little radius squared times the thickness. Now I drew this one standing up, so if this were from a graph, this one would be dx. If the washer were lying down, then it would be dy. So let's do an example. Take the area bounded by y equals x squared, y equals x, and y equals 8. Rotate it around the x-axis and set up a volume, an integral for its volume. Let's change this to 9. We want that to be a nice number. So let's see, let's see, y equals x squared. That looks like this. Y equals 9 is this. So we're taking the same area, or this area here. It looks similar to the one that we had earlier. But we're going to take that, and this time we're rotating around the x-axis. So you rotate around the x-axis and you get this. And the way the disk is going to look is you pick some value of x in here, and you draw the disk there. Don't draw the disk over here, and don't draw it right on the end. Draw it somewhere in the middle. And I know I'm calling it a disk, but it's a washer. So I'm going to go from there, and I'm going to go straight up to here on the curve. I guess it's the line. And I'm going to draw the outer part of the washer there. So that's my washer, and it's going to have a small thickness. This is a pretty horrible drawing. But anyway, that's my washer. Let me color it in. I'll color it in red. So this is my washer, and I've got to come up with the volume of this thing. So what I need is the little radius from here to here. Then I need the big radius from here up to here. All right, in this case, the big radius is 9. Now, if we wanted to get fancy, we could say this is the point, its x-coordinate is x, and its y-coordinate is 9. This point here, its x-coordinate is x, and its y-coordinate is x squared. So the little radius is x squared, and the thickness, well, the thickness is a tiny, it's how wide this is. So going from one side of this to the other, it's a tiny change in x. So thickness is dx. So my volume is going to be pi times the integral of big radius squared minus little radius squared dx. And we go from 0 to 2. Or no, I'm sorry, we go from 0 to 3. Because this point back here is 0, 0. This point up here is 3, 9. So that's our integral. All right, my drawing there is pretty awful. So let's look at the computer drawing. Let's see, the function we had here was x squared. Well, on top we had the function 9, y equals 9. Then we had y equals x squared. And we're going from, what was it, from 0 to 3. So we're taking this area here. Let me zoom out so we can see it. We're taking that area and we're rotating it around the x-axis. So we get this. Let's turn the opacity up. So we're getting this thing. If you turn it on its side, it looks kind of like a stadium or something. And if we look at the different, washers inside of here, start off back there. I guess that first one might be solid. Yeah, and then they get as you get closer and closer to the top, they get smaller and smaller. All right, so let's go back and work the integral out, and then we'll compare it to the answer that the calculator there gives us. All right, so this is pi. Let's see, when I multiply this out, 9 squared is 81. X squared is x to the 4th. So you get pi times 81x minus 1/5 x to the 5th. We're going from 0 to 3. So let's see, it's pi times 81 times 3 is 243. Let's see, 3 to the 5th is also 243. So let's work that out. I'm also going to double check that 3 to the 5th. Yeah, 243. So 243 minus 243 over 5. That gives me 972 pi over 5. And what is that approximately? 194.4. Wait, 194.4 pi. If I do that, I get 610.72. And if we compare that to, oh, I'm sorry. Oh, no, that's, for a second I thought that was invisible. All right, let's compare that to what the computer got. 610.9 and 194.46 pi. So 610.9 versus 610.72, not bad. The thing is, this is exact. This is an approximation to being exact. The the calculator's decimal approximation by multiplying by its approximation of pi. The computer, when it does it, it's doing it numerical the whole way through. All right, let's look at this next example. It says repeat the previous example, but this time rotated around the y-axis. Okay. So in this case, we've got. I'm just going to go ahead and draw it. We're taking this area in here, shaded in orange, because orange is my favorite color. Right, if we rotate that around the y-axis, then we're going to get this thing. And the disks for it are going to look like this. Notice in this case we get disks instead of washers because the whole way the area lies right against the axis of rotation. So in this case we're going to get, let's see, the thickness is dy. And let's see, we need to go from here to here. So we need these in terms of y. Now, the y-coordinate of this is just y. What was the equation? Y equals x squared. Yeah, y equals x squared, so we could also write this equation as x equals square root of y. And then this point over here, this is the point, it's got the same it's x coordinate 0. But it's got the same y coordinate as the other one, so its y coordinate is also just y. So my radius on this one is going to be this length here. So that's going to be the difference in the x coordinates of these 2 points. So it's going to be square root of y minus 0. All right, so the volume here is pi times the integral of the radius squared dy, the thickness. And what are our endpoints? Our endpoints on this one are different from before because now we're doing it in terms of y. At the bottom of the thing, the y coordinate 0. At the top, the y coordinate is 9. And I was going to say let's just set this one up, but this is such an easy integral. Let's do it. We got from 0 to 9. Square root of y squared is just y dy. So you get pi times 1/2. Let's see, pi times 1/2 y squared from 0 to 9. And so going into the next page, let's see, pi times 1/2 times 81. So 81 pi over 2. And as always, I want to check. All right. So this was y equals x squared. Well, I guess I didn't even need to change anything here. We've got that area, and now instead of rotating around the x-axis, we're going to do the y-axis, which is x equals 0. Rotate that thing, and we get 127.33 or 40.5, etc. pi. Now the exact answer that we got was 81 pi over 2, and that's right at half of 81 there, 40.5 something. All right, so we'll stop here.